Until 93, Viterbi decoding plus Reed-Solomon code, we approached channels limit by 2.5 dB. So we had already kind of 6, 7 dB. And even at this time, we worked already on iterations between the Viterbi and the Reed-Solomon decoder. Iteration, and you could gain another 1.5 dB. This was motivated by the failure of a spacecraft where the antenna did not fold up, and then we tried to gain another dB or so to receive data. And then at the same time, 93, Beroux-Lavieux and Tidimashima came up with this with a stunning result. They approached channels limit by 0.5 dB. You see, it's like with the absolute zero temperature in physics. The closer you get, the more difficult it becomes. And finally, you are fighting for tens of a dB or something like that. Okay, later, 2 years later, Beroux and his co-workers came up with turbo equalization. So they showed that you could also apply this turbo process to equalization, and I believe it was around 97 that this principle was named and recognized as a channel limit. Today we can approach channels limit as close as we want with practical codes, but still, of course, we need a lot of block names. Here you need 10 million bits or so in one block, so it's not practical to go so close. But we have now, in this time, we have reached the goal. By the way, ask questions whenever you like. So the turbo principle, as I would define it, you need a communication system which has a serial or parallel concatenation of components. And I claim every communication system has at least a concatenation. For instance, you have a cyclic redundancy check and an error correcting code. You have a code and a multipass channel. You have a code and a mapper, and so on. So you have source coding and channel coding. So these are also a concatenation. That's what you need. And you need detectors and decoders which calculate a posteriori symbol by symbol detection. A posteriori probability symbol by symbol detection, like the Viterbi algorithm, modified Viterbi algorithm, the SOFA, or the BCJR, Bal-Jelinek-Raviv algorithm, which has been also forgotten for a while. And soft-in, soft, you need, in short, you need soft-in, soft-out decoders. We are not making any more hard decisions, but we decide probabilities, or soft values, as I will explain later. You need to have statistical independence, because when you have bursts, the next stage cannot operate probably. So you take some kind of scramblers or interleavers in between. And here comes a very important concept, the so-called extrinsic information, which I will explain with a simple example. So this thing really constitutes the turbo principle. All these elements together have the turbo principle. Well, turbos are known in cars, as you know. When you buy a BMW, I hope you do, because it helps our economy. The turbo engine is better. So this is the main engine here. This is the main engine of your car. The fuel goes in here. And not all of the power is used to power the wheels of your car. Part of the power is used to power a turbine. That's where the turbo comes from. And this turbine really gets fresh air in, compresses it, and hot air flows into the machine. So there are two machines, and not all the power is used for output. You take part of the power away to power the turbine. But both together, they work much better. On the German Autobahn, when you have a turbo, BMW can go much faster than anybody else. Right? So everybody knows turbo is better. So that's the final proof. Also in communications, we have now the same thing. We have two engines, two decoders, serial, maybe a Solomon decoder and a Viterbi decoder, or parallel, whatever. Here are the interleaver, pies for permutation, scrambling. And now the fuel which comes in, is the transmitted received signal, right? Match filter output weighted by channel state information goes in the first decoder. This one does not make a decision, not a final decision. It outputs log likelihood ratios or probabilities, sends it to the other decoder. This one works. Another constraint of the whole system sends back its opinion here, and now the two iterate. They help each other out of the noisy environment here.
What is the physical meaning of the interleaver?
The physical meaning of the interleaver is that most decoders cannot handle bursty structures, bursty noise or bursty error. So the physical meaning is just you rearrange your bits. So that causes delay. Right? That causes delay. But you see, in mobile or wireless communication, most of the delay comes on the transmission. So this delay of the iteration is not important. But you have to transmit the whole frame before you start. Delay line is nothing else but a kind of convolutional code. Or you could have two serial concatenated codes, Reed-Solomon, as I said, and Viterbi, like in many satellite transmission systems. Or you could have a bit interleaved coded modulations, and the outer one is an encoder, and the inner one is a mapper or demapper. Or you could have a MIMO channel here. MIMO channel here, then you have a MIMO detector here and an error correcting code outside. And then you do iterations between the MIMO detector and the error correcting code in this tool. Or this could be a source encoder. For instance, we did work in GSM. The GSM encoder here still has some redundancy in the compression, so there's some memory in it. And here's a channel encoder, and then you can do iterations between the channel decoder and the source decoder. And you gain 2 dBs or so if in an existing system. But of course you have to do more processing. Or low density parity check codes, which are so popular those days. So the outer code is a check node, and the inner one is a variable node. So, and there are many more such
I like to work with log likelihood ratios and to have the binary values in +1 and -1. So +1 is a null element under the GF2 addition. Now a log likelihood ratio is a probability that the bit is +1 divided by the probability it has the other value and the natural logarithm. You can invert this formula as you can see here. And the nice thing is now we have a real number. We are going back to analog. We're going away from digital and binary. We go back to analog. This is a real number now, because if this is equal probable, you get 0. If this is more probable than this one, you get a positive, and vice versa, you get a negative value. So a +5, for instance, is a very reliable plus, and a -0.2 is a very shaky minus, right? So we have the probabilities in here. So the sign of this is a hard decision, and the magnitude is called the reliability. And all turbo decoders work not with bits, with hard decisions only, but also with reliabilities, which are exchanged. And now another notation, a so-called soft bit. What is a soft bit? A soft bit is the expectation of this bit plus minus 1. So it's very simple. It's plus 1 times the probability of plus 1 plus minus 1 times the probability of minus 1. Remember, we had all these exponentials in here, in the inverse formula. So the hyperbolic tangent pops up here. It's a sigmoid function, as you know, and it transfers the log likelihood ratio to the soft bit, which is now in the range of plus 1, from minus 1 to plus 1, right? So that's a soft bit. Now, one of the basic operations in any parity check or in any code is you have the sum of two bits, the XOR sum of two bits. Of course, minus times minus is plus, so you can also represent it when you look at it as real numbers, as a multiplication, but it's still the representation of the XOR. Minus times minus is plus, and so on. And now we want to get the expectation, and if they are statistically independent, you multiply the expectation, so you multiply this one, and this leads to the soft bit of the sum of two. Now if I want to have the log likelihood ratio, I just invert my hyperbolic tangents the way back, and then I get a rather complicated formula, take the log likelihood ratio of bit number 1, bit number 2, nonlinear, transform it into hyperbolic tangents, multiply it, and invert it. And this is a long formula, so I invented a short abbreviation for it, which is called the box plus, right? And the box plus, a good approximation you can keep in mind is the sine of the two. You see it immediately from here. The resulting sign is the multiplication of the two signs, and the magnitude is the minimum of the two magnitudes. That's quite clear, because when you have an unreliable bit, the result is unreliable, right? In adding it to another bit. So the result of log likelihood ratio of the addition of two bits is magnitude is the minimum of the two magnitudes. And now when we transmit, now we have a posteriori probabilities. We transmit over, say, a fading channel. X is plus minus 1, this is a fading factor plus additive noise, and we want to maximize the probability that X given us the received value. No coding yet, it's just simple by simple transmission. Use Bayes' rule, use the PDF of the Gaussian channel, and plug it in and do a little bit of calculation. And what the outcome is, the conditioned log likelihood ratio, the a posteriori probability log likelihood ratio, with these probabilities now, is the matched filter output, is a Y, weighted by the sum. In the Viterbi algorithms, the weighting is not important, but here it is important. You weight it by the channel state information, right? So if ES over N0 is high and fading is good, so you get a high value. If you have a deep fade, you get a deep value. And in addition, because of Bayes' formula, you get also a priori information. You have the a priori. If somebody tells you that the plus minus 1, the plus 1 is more likely than the minus 1, you should use this information. We usually assumed equally likely bits, but that's not the case in many applications. So in addition, you add up the a priori information. And in turbo decoding, this a priori information comes from the other machine, right? So if the one machine works on this one, it gets a priori information from the other machine, and its output is then fed back to the other machine, to the first machine, and you get use this later on as a priori information for the other. Or if you have statistically independent transmission, like in diversity, of course you have to add up log likelihood ratios. The probabilities multiply, so the logs add. So you have all the information, you add it up. Let me give you a simple example to make this more meaningful. You can use it also in practical life. Did it snow in New York City this morning at 8 o'clock, right? Snow means +1, transmitter +1. So I had two detectors in New York City, X1, which measured +1, X2, which measured also +1, right? Two detectors. And also I have a priori information available. I looked in the long-term statistics of snow in New York, Farmer's Almanac, or I don't know what it's called here. And the probability of snow on the 13th of February is 75%, long-term statistic. So I have a priori information on top of my, so the log likelihood ratio of 75% is plus 1.1, right? And now I transmitted, my first transmitted, but it was received as minus 1.5 because there was noise on the link, right? Right, so this was transmitted, this was received. I multiplied by the channel state information, by my link quality, I get minus 3.0. Link number 2, I received randomly 0.09. Channel state information was 3, so I have 2.7. And now I have to add up all 3 results, right? From one transmission, from the next transmission, and from the a priori knowledge I have, because this should influence my final decision, right? If I should take all the information I have. And that's important in turbo. You take any a priori information or anyone from the other decoder to improve your decision. And now it's quite clear what you have to do, add up all 3, so you get plus 0.8. And when you transform this back in probabilities, you know even it's a plus, so it's no in New York, but with an error probability of 31%. Right? Like in the weather forecast, you don't have a sure forecast, you have a certain error. So that's the meaning of this log likelihood ratio. Now we use it for error, for decoding error correcting codes. When you have a parity check equation, you know that each bit is the sum of all the other parities. And now, if they are transmitted statistically independent, you know immediately what the log likelihood ratio of this one is. It's a box plus sum of all the received values here, right? Whenever we have a XOR, like here, binary TF2 addition, with the log likelihood ratio, we have to do the box plus. So it's very simple. It's the best decoder you can do. It's a a posteriori probability decoder. And now you have a second opinion, say, about bit xi. Of course, bit xi is also transmitted, but you get a second opinion from all the other bits. And this is called the outside, the extrinsic opinion about this bit. Of course, bit xi is also transmitted, so you have also a received value for bit xi. And this is called the extrinsic information. All the other bits have been transmitted with a certain reliability and certain decisions, but they give you an opinion about bit number I. And this is called the extrinsic. Let me give you an example, a single parity check code. I received 2 values, minus 0.3 for bit number 2 and bit number 3, minus 5.5. Now the extrinsic log likelihood ratio for the first bit is a box plus of those two values. Box plus means roughly multiply the sign, so it's plus, and takes the minimum of the 2. Right? Now this means that the 2 other bits have the opinion that bit number 1 is 0.03, right? And this is the extrinsic information from this decoder. If I have now a parallel decoder which works on the same bits, I can use this as a priori information in the decoding process of the pattern. Is this clear? Because these are the basic elements. Prakash.
What happens if that A is not known? It was the...
If the channel state is not known. Well, you can also derive log likelihood ratios with unknown states or non-coherent, for instance. There are many ways to derive log likelihood ratios.
And they also have this nice form?
They also have this nice form, yeah. Yes, please.
If you pass this decision on to the next scalar as a priori information,
Yeah.
but if it's an error, isn't that error going to propagate?
Sure, but usually what you get, that's a very good question. You see, when you use hard decision and you have hard decision and not shaky values, right, then the other decoder has to take the hard decision. Here, for instance, it gets a very weak decision, right? This decoder says, well, I'm not so sure, it's probably plus, but with a very weak reliability. But still it helps. The worst thing is you use only the sign and pretend you know that this is plus. You don't know it. Here's the probability that it's minus is fairly high, right? So that's what typically happens when the decoder makes an erroneous decision. It has a low reliability because it was close to the threshold, right? So one always should feed back, that's also true in interference cancellation. Never feed back hard decision, you should always feed back these soft values. Because when you make a wrong decision, usually the reliability of the wrong decision is smaller. Yeah? Okay. So I think these basic things are very important. Now with this, you can already decode a low-density parity check code. If you have never decoded a low-density parity check code, you can do it now. A low-density parity check code has these coded bits here, and here are the parity check equations. Right? So the XOR sum is 0, so the log likelihood has to box plus. Right? And what a low-density parity check code is, you have connections here. And here I have a so-called irregular low-density parity check code. There are 3, 2, 5, and 3 connections here. A regular one would have the same number of connectors here. And here you also have. So, of course, the number which goes in here has to go out here, and you have wiring in here. Right? It's just a wired network. And the art of designing a low-density parity check code is just to put in those wires and nothing else. And now we know what we have to do. You see, when we receive values from the transmission of all bits, these are this LC times Y, we feed them in here, and they propagate, and when they go out here, what we do, we calculate the return. The return, it's called message passing, the return log likelihood ratio is a box plus of the two other ones, right? Like in the example I showed you. Return is a box, so each line is double. You have ingoing and outgoing messages. And so the outgoing message, for instance, here is a box plus sum of these two. And they are now relayed back here, and here you have the algebraic sum, because this is now assumed to be independent knowledge about this particular bit here, coming in from all this information, and now here you sum it up. Of course, after a while, it will not be statistical independent, but we assume it is. And statistical independence means you add up the log likelihood ratio. So what are the formulas? Here you have to add up the log likelihood ratio. Here you have to box plus them. Right? So you can do it this afternoon in your MATLAB computer and decode your first low-density parity check code. You see, use this formula. The output here, the final decision on this bit is the incoming one and the extrinsic information which comes floating back from the other side. So all these which float out here, you add them up, and you you don't take the ice one. And on the other side here, you take the outflowing is the sum of all the other ones in the box plus sense, right? So it's very easy. And actually, we are building this network with analog devices, because it turns out this box plus can be realized with 9 transistors, with a Gilbert multiplier. And so it's very nice to build this whole network. It's a nonlinear, highly parallel network. You load it with the incoming thing, and then it floats freely and gives you the result. So we are going back to analog. Continuous time, continuous value. I will not talk about this here. Now let me show you how the classical turbo code of Peru worked. The classical turbo code of Peru was what we knew all the time, I guess Shannon already knew it, is that you have an array code, right? So you have information bits here, you plug in parity bits here for each line, and then you do the same thing again, so with the same information, it's now interleaved, it's a simple row interleaver, and you get the parity bits here, right? You don't take parities on parities here, you could, but you just lose redundancy here. And now the turbo decoder first decodes horizontally, right? Right? Think of a single parity check bit as I did it before, and then you write the values of the result, the extrinsic L values, you store it here. And now when you do vertical decoding, you have already a priori information, like from the Farmer's Almanac, right? Somebody has done the horizontal, and this is the a priori information now for the vertical. Now you do much better, because you don't have only the received values, which are in here, but also a priori information for each information bit. And this you add to your information, as I did with Farmer's Almanac, right? Remember? And then you do vertical, and vertical you write it in here, and so this is the extrinsic result of the vertical. Up to now we have statistical independence. So we are really, if we want to get the final result, we would add up this one as an information, and this one. And now we use this one as a priori and do horizontal again. And now we get somehow statistical independence. And then analysis becomes very complicated. And then we go on, and we might do 20 iterations, if you like. And finally it settles down, and the process is still not fully understood. It's a highly nonlinear feedback process. And so control engineers, I guess, and control theorists should look at it at this.
So can I ask you a question about that point? Right from the beginning, it smelled of a fixed point theory in...
Exactly, yeah.
So has anybody proven that this process converges?
Yeah, for very simple codes, for very simple like the repetition codes or a simple parity check code, you can prove that a fixed point exists and you can approach it. But if it's more complicated, it's a search in a multi-dimensional. You see this is a dimension of the problem, right? Say 20 times 20 here, 400 dimensional problem, and you search for the global minimum. And as usual, this is not so easy. Right? Let me before, yeah, Prakash?
When you iterate between the two, it's actually the dependence that helps improve the estimates at every round.
Right.
Yet in the calculation of the log likelihood, there seem to be independence.
Exactly, yeah. So, yes, there have been attempts to include some correlation. Of course, you can only add log likelihoods if it's statistically independent. And it's only statistically independent in the first two.
Right.
And later on, of course, you use the information twice. That's why you only should use extrinsic information. So, for instance, for a particular bit, you take only the opinion of the neighboring bit, not the bit itself, because otherwise you would use this twice. Yeah. So you try to be statistical. I guess I have a demonstration which I would like to show you to show the chaotic behavior of this process. Let me show this. What you will see is I have a matrix 20 times 20, right? Can somebody stop this again here? 20 times 20, so I have 400 information bits. I use a RAID 1/2 code, so I have 800. 800 I transmit with a soft in, soft out Viterbi algorithm. I decode with this one, and I will show you not numbers, but I will show you correct bit as green points and erroneous bits as red points, right? And the diameter of the circles I will show you, of the points, is the reliability, right? The diameter is the reliability. And that means that we, at the end, we would like to see big green circles, right? Right, 400 big green circles, because the big circles show it's a reliable decision and it's also a correct decision. I guess we try to fix the cable a little bit. Okay, now leave it. Oh, it's better now. Okay, so let me show you. I have to start the simulation. It's now an online simulation. Come on. No? Now something doesn't work. Okay. It's always when you try to show something. I don't know, I checked it this morning. Okay. I guess I made a mistake here. Okay. So it's iterative decoding of a two-dimensional convolutional code. So in each direction we have convolutional codes, and I take memory 2, and I have 400 information bits, but I have to terminate it, so I can only allow 398 because of the termination. And now I transmit 800 bits, right? Because it's rate 1/2, and say I go from 3 to 5 dB in steps of 1, and I have Rayleigh fading, right, on the channel, and the rows are 20 by 20. All parameters are okay, I hope. And now I start a random seed of the random generator.
What does memory 2 mean?
Memory 2 convolutional code. It's a standard convolutional code. It's a textbook code, I guess, or all students should know it. Okay, now what you will see, a correct decision is a green circle, right? A wrong decision is a red circle. And now I do iteration. When there has been an error at this position before, and this error is now corrected, you get a shaded green, right? And the worst thing which could happen, there was no error at a certain position, and now in the next iteration, you get an error. And that happens sometimes as the coder tries several patterns, right? And keep in mind the diameters are proportional to the reliability of the decision. So at the end, we would like to see huge green circles, right? Let's see what goes on. So this is just some housekeeping data. So we have now Rayleigh fading at 3 dB. Everybody knows this is a very noisy channel, Rayleigh fading at 3 dB. And I transmit the first frame, so you should see those 400 bits. Here they are. So this is now what you get from the channel, right? Log likelihood ratios from the channel, meaning matched filter output weighted by the channel state information. Here the Rayleigh fading was mild, so you get huge values. And here you see the errors, that was your question you had before. The errors are usually very small, right? So these are weak errors. And sometimes you also have a real strong error. And now I do iterations horizontally. And you see what happened. Some bits were already corrected, right? And I go on vertically, horizontally, vertically, horizontally. And you see all kind of movements in here. In the iteration, it's a kind of chaotic behavior, and you see it does not converge now. It's still going, trying several things. Or in the multidimensional plane, it's moving around and tries to find the minimum, right? But we have already very strong patterns. You see, for instance, in this direction, vertically, this is a valid path in the trellis, right? So it took this valid path, but it does not match horizontally, so it takes a while. I was sitting at an airport recently looking at this, and a businessman said, "Oh, I didn't know this computer game here." But it's serious, you learn a lot about this. You see, okay, I don't think we will make it this time, because the signal to noise ratio is too bad. But it's not the end of the story. As long, it's like in normal life, as long as action is going on, there is hope, right? As long as action is going on, there is hope.
So if the parameters are kept fixed, then you just change your random...
No, everything is, I do the iteration, so the a priori value changes all the time.
If you change your seed number, will you observe sometimes converging behavior and sometimes not?
If I change my seed, yeah, sure. It depends on the randomness of the transmitted thing.
Sometimes it will
Yeah, let me do another one. Let's go to the next signal to noise ratio. Right now I go to 4 dB and transmit another frame. Now you can play turbo poker. Can it decode or not? Put $1 on the table, right? And we can play poker. Can it decode or not? I don't show you the parity bits, right? I don't show you the parity bits. That's why there's some randomness in it. You cannot count just the errors. Now let's see how this is going on. Oh, it's doing much better, right? Now you see this was vertical, and in the next horizontal iteration, look at this, there's only a single error. So my guess, that this will be corrected in the next horizontal, right? Because a memory 2 convolutional code can correct any single error. You see what happened? It transformed it to 2 weak errors, right? Now we are done, right? So that's the end of the story. Okay.
So it doesn't guarantee convergence.
It doesn't guarantee convergence. And sometimes you make errors. Of course, this is not a machine which is error-free. Sometimes it really makes errors. Of course, we have a finite block length, so we are not error-free according to Shannon. Okay, now this starts again. What is this? I guess I hit the wrong key. Let me finish this task. I'm sorry. I need to go back to my program. Okay. Okay, let me go on with my talk. Now I will try to explain you the exit chart, which is a tool to analyze this chaotic behavior on an average basis, not on an individual basis, but on an average basis. So if the matched filter output is Gaussian, with this one, plus minus A from the fading, then you can show that the a posteriori log likelihood ratio, which I showed you before, is also Gaussian, but it has a nice feature that there is only one free parameter because of this normalization. So the mean value, or the magnitude of the mean value and the variance are closely connected. They are a factor of 2. So that's nothing, no mystery, it's just the consequence of the normalization. And it also is symmetric, meaning the minus and the plus are treated equal, so we have and this, people call this a consistency condition. All proper log likelihood ratios have this condition, and this allows us to calculate mutual information between the input and the output log likelihood. This is Shannon's formula applied to a binary input channel, mutual information. And you have the probabilities, that is +1, that is this probability here, the Gaussian. And after some manipulations, you end up, you just have a nonlinear transform of your L value, of your log likelihood ratio, to get the mutual information. Now, after decoding, the distribution is not Gaussian anymore, because a Viterbi decoder, for instance, is a nonlinear device, so we don't know this distribution. But we can evoke the, and this is our contribution, you can evoke the ergodicity theorem and just do averaging of these nonlinear values, right? And then you get the mutual information. It's a very nice way to calculate mutual information or to measure mutual information. So we have a measurement device which measures mutual information after a decoder. This is now only the horizontal decoder. So our encoder, our channel, our decoder, and here we get LE, we do simulations with this one, and then you correct, you can only do it in simulations, you correct with the known bit, and then you measure the mutual information. And this is a vertical axis in the so-called exit chart. And now the horizontal axis is the a priori information which comes from the other decoder, right? Which comes from, and we model this a priori information like the transmission over such an additive wide Gaussian noise channel, similar to this one, and feed it in. And now by changing the noise, we can change the mutual information of this channel, right? So this gives us a horizontal curve, the horizontal axis in the so-called exit chart. Exit chart is extrinsic information. I guess I skipped this here. Exit chart shows the mutual information of the a priori channel coming from the other decoder and as an input, and the mutual information of my current decoder, where X is the input and the extrinsic is the output. You can do it for the single parity check code, as I showed you before, and the result is this one. So this is the first exit chart, because the extrinsic information, as you know, is a priori information plus channel, Farmer's Almanac plus transmission, box plus with the transmission of the third bit. And then you get the extrinsic information of the first. Plug it in your nonlinearity and you get the vertical axis. Plug this into your nonlinearity, you get the horizontal axis. And now we have, you see what, there's a meaning behind it, because it's measured in bits. I can transmit 1 bit, so the value is somehow between 0 and 1. If I don't have a priori information, my parity check code gives me roughly 55% or 52% of a bit. If I give him some a priori information, I get a little bit more, right? And now I swap the 2 axes. This is the 1-to-1 line, because the other decoder takes this now as a priori, so the iteration would go this way, this way, this way, and it would get stuck here. A single parity check code is not very good in turbo decoding, so it gets stuck here. We would like to reach the point here where we know everything about the bits. Mutual information 1, so everything comes over, right? Okay. And now, in general, exit charts always look like this one. So this is now an exit chart, say, of a multipass channel. A multipass channel, you can also calculate the exit chart. So this is this curve. And the channel code is this curve. You see, since the channel code is the outer, it does not get any input from the channel, so it starts at 0. So all the a priori information comes from the inner decoder. Whereas the outer one gets already some. And now iteration would start and go up and down here until it reaches this point. It's a nice property which has been proven recently, that the curve under the channel or multipass channel is a capacity, and the curve under this here is the rate of the code. And that means, again, we can show when the rate is smaller than the capacity, we do not cross, and we have Shannon's formula again in a different setting. So what we would like to design when we have a certain channel, like a multipass channel or a MIMO channel, we have exit charts for MIMO channel, we try to adapt our outer code in such a way either to get a few iterations, then it should be down, or to be as close as possible, and then you have a very narrow tunnel, and then you inch through this narrow tunnel until you converge. And so this tool, I believe, is very powerful, and I give you an example. The inner is a multipass channel, modulation, BPSK, signal to noise ratio with 4 taps, and that's the result of the multipass channel, right? Exit chart. And now we have a set of codes, rate 1/3 up to rate 8/9, I believe. And you see 8/9 code would not work because it intersects. Even the rate 1/2 code does not work. This is the rate 1/2 code because it intersects here. So the iteration would start and get stuck here and not reach the upper points. So you can use this exit chart, and it has its information theoretic meanings. That's a nice thing. And you can also use, I'm going a little bit faster now, you can also use irregular code. As in low density parity check code, you have a set of codes, rate compatible punctured codes, for instance, with several rates from 1/3 to 10/12, and then you take a certain percentage of each code, and this allows you to massage your exit curve, because it's the sum of this one. And that gives us the following result. We allow an average rate of rate 1/2 and get the blue curve. The only rate 1/2 curve would intersect here, but this one does not intersect, and then we can inch through the tunnel, and the iteration will converge. Right? So you can design really a set of codes which approaches your channel curve here, or your inner curve. You can do this with QAM modulation. Now in QAM modulation, the outer code is any of these codes I have shown you. The inner one is not a multipass, but it's just a mapper, QAM mapping. And then we do the iterations here, and we design the whole system with the exit chart. And now a nice thing or interesting thing happens. The gray mapping does not give you any gain here. The gray mapping, because in gray mapping, say if you have 4 bits with gray mapping, knowing 3 bits doesn't tell you anything about the 4th bit. But there are other mappings where you get knowledge knowing the other 3 bits. And this is a knowledge in information theory terms you gain with the exit chart. That's a particular mapping which I will not go into details here. And now we have this channel, right? Including the mapping, Z16 QAM, including the mapping. And now we are looking for a code, like for instance this one, and now we have our iterations. You can count 1 iteration, 2, 3, 4, 5, 6. After 6 iterations, it converges. And that's a nice thing. Well, there's a slight problem here. The channel does not go to 1, 1. So we have an error floor or a residual error rate. So we, even with perfect a priori information, we don't get perfect extrinsic information, right? There's a remedy against that. You use pre-coding, so-called differential pre-coding, and then the curve looks like that. You see it goes up to the point 1, 1, and now the iteration goes like that. And we have shown that if the interleaver is large enough, so you get good statistical independence, then these exit charts really, these are real measured iterations. You see, it does not fit always exactly, but it fits very nicely to these pre-calculated or pre-measured exit charts. So I think Stefan Dimbrink did a real good job with these curves. And here, this is just an overview of all these QAM. You see, this is Shannon's capacity with 64 QAM and so on. And the red curve is what we achieved. We come very close to capacity in a wide range of signal-to-noise ratio. Now MIMO, well, it's the same principle, whatever you have. Now the inner channel is a MIMO, and here comes the outer interleaver and convolutional outer code. The MIMO channel takes a block of n and mapped to a QAM system of with m bits, 2 to the m QAM. So here's a mapper, and here's a space-time MIMO code, whatever it is. Could be only blast. And here you receive it. And now you have the problem to find a soft in, soft out. We want to get log likelihood ratios out here, right? Not hard decisions. Log likelihood ratio. And this is complicated because the complexity goes up. Say if you have 64 QAM and 8 antennas, then you have just too many possibilities. So what we are working right now, we use a sequential decoding algorithm, which is a very old means in error correcting coding, and we work not on a trellis, which has too many states. We work on a tree, and I will only indicate what you have. Here is a channel model, right, with this Rayleigh fading channel matrix here, and we have these ergodic coefficients here on the channel, which vary from one frame to the other. And now the soft output, you can write it down. It's no problem to have the optimal soft output. The log likelihood ratios of bit m, of the mth bit in the nth QAM symbol is this here. That's the optimum thing. But you have just too many possibilities for these x. You have 2 to the m, capital M times n possibilities, and here you have to take all the ones which are +1 at this position. So you have just too many. There are several search procedures like the sphere decoder and others to find the valid ones, because you need only those which gives high values here. And say if it's 32 QAM with 4 antennas, you would have to use 2 to the 20. So the problem is just too exhaustive. So we have to do a limited search, which we do with sequential decoding, and we apply Cholesky factorization to get a triangular matrix, which allows us to have an additive metric, which you need in sequential decoding. So you have this metric with the coefficients from the decomposition here, and then you use a sequential search with a stack algorithm, and then you get a soft a soft log likelihood ratio for each bit, which you pass to the outer decoder, and the outer decoder, I'm almost finished, and the outer decoder, you see, it brings in a priori information. Here comes in from the outer decoder the a priori information which goes into your algorithm here. You see it's here, this is the a priori information, the farmer's almanac information here, and then you use it in the iterative process. And here's an example that shows that you do not need, that's a very simple example, you do not need 256, you only need 10 candidates, and you get a performance which is from Shannon's limit away at 10 to the minus 5, 1.4 dB or so. So you can, Telatar has told us how to calculate Shannon's limit for these MIMO channels. So you can apply it also here. Well, let me finish. The turbo principle is a very general principle, and I guess you will easily realize that we always have some concatenation. Is it serial or parallel? And the extrinsic information, that's the important thing. You can approach capacity limits by using a huge interleaver, and that's also a drawback, of course. And for systems with a high number of states, we have recently developed a new sequential soft-in, soft-out algorithm when the Viterbi or BCJR algorithm fails. I have shown you 2 or 3 applications, but you can do turbo-source compression also. It's the same principle. You can do joint source and channel coding. You can do multi-user detection. So, well, MIMO channel is a kind of multi-user detection. So the inner one is a multi-user channel, and the outer one is the error correcting code. For interference cancellation, and I already have mentioned, you can implement the whole thing also in analog VLSI, and then the number of iteration goes to infinity, because analog you don't have any timing. It's just flooding the whole network in continuous time. So I believe there's a lot more work to be done in this area. Thank you very much.
The exit chart requires knowledge of the channel. Is that correct?
And requires statistical modeling of the channel, yeah.
So, but it's a deterministic model. So if it's a convolutional channel, you need to know the coefficients.
You need to know if it's a convolution, you need to know the coefficient. If it's a multipass channel, you also need to know the coefficient. But there's also what people call a turbo channel parameter estimation. You see, the more you know about the detected bits, the more green circles you have, right? Green circles mean you have correct bits, right? And they are training bits. So what you do in the turbo loop, more and more bits are converted into training bits, and then you can re-estimate your channel from one estimation to the other. That's a very important feature, because initially you can have a preamble and measure your channel, right? But also during the iterations you get more and more green circles, right?
So from a code design perspective, if you know the statistics of the channel, is there a straightforward design process, or?
Yeah, well, I have shown you one example with these irregular codes where you can massage the curve and match it to the curve you got from the statistics of the channel. Yeah, there's a design procedure to adapt the error correcting code to the channel or to the inner.
So to what degree, I'm getting the impression by having seen the literature, lots of uses of the turbo principle in various applications and various models, that to some degree there are heuristics. I mean, people say, let's try this principle and then study the performance. Is it how well it converges or not? How much has been shown theoretically, with what constraint, what models?
Okay, what has been shown, really proven results exist only for the binary erasure channel. When you have not a Gaussian channel but a binary erasure channel, and with low density parity check code, Urbanke and these guys, they have shown when does the whole process converge, and that it converges to Shannon's limit. And
So that's the only place.
that's also you can get also analytical results for the exit charts for the binary erasure channel. I didn't show you.
That will be achieved in Hagenauer paper.
Yeah, yeah, yeah. So Ashkimi and exactly these three people. Maybe I can go back and I skipped the slide.
Well, where is the difficulty when you try to prove convergence in other models? Is there something that one can pinpoint and say, this is where the attempt to prove convergence gets tough? I mean, is there some general statement one can make?
Okay, if you would be able to calculate the exit chart from the channel statistical and the code parameters, if you would be able to do that, and you are able to do it for binary erasure channel, then you can prove it converges or not for a huge interleaver. Right? The problem is you have an interleaver with 400-bit, proof of convergence is complicated because you lose statistical independence. Right? So proofs can only be done for huge interleavers, where you assume statistical independence. And look at this. What really has been shown, if you take the test channel here, this is a test channel which generates the a priori information. If you take not an additive white Gaussian noise channel here, but a binary erasure channel, then you can calculate for several codes, you can calculate the exit chart. Because when you use a test channel, I skipped this slide, when you have a binary erasure channel, it shows the mutual information is nothing else, with this formula I showed you, is nothing else than 1 minus epsilon, which is a textbook problem. So, and then you can do some calculations here, but not, to my knowledge, there are now some attempts. We have also worked on that for the binary symmetric channel, even with convolutional codes. Jack Wolf has worked recently on this, but not for the Gaussian channel.
And yet, a robust, good behavior is observed for a wide variety.
Oh yeah.
Anybody has offered explanations of that robustness, or tended to explain what's at work there that makes it looks like magic, right? In the beginning.
Yeah, well, it always converges. Yeah. Well, you know, you can when you use a factor graph, when you look at the factor graph, you want to minimize the curve, maximize the curve. So to avoid, so the message should go a long way until it comes back, right? The message, so it should be statistically independent. Don't use the same result immediately in the next decoding step. Yeah, but I believe control theorists should look more closely, but we do this analog decoder, and there we solve nonlinear differential equations, sets of nonlinear differential equations, and you have some results from this theory to prove convergence in certain cases. But it's going back to analog, right? Feedback, analog, and all these things.
More questions?
In your second to last chart, you had 256 QAM, but you said because you were doing sequential decoding, or maybe you had an extra chart.
Yeah.
It indicated maybe you only had to pay attention to the 10
Exactly.
nearby.
Yeah.
Okay. I just
Yeah.
wondering if I got that right.
Yeah. So typically you cannot look at 2 to the 20 possibilities, but it turns out you need only 2 to the 6 or so. Yeah. The problem is you try to search all possibilities in a clever way, so you get only those which are close, say to the inverse solution or things like that. So you take, yeah. And sphere decoding is nothing else. They look at algebraic, but here we have a structured search in a sequential algorithm.
More questions? As you know, the practice is that in the afternoon from 2 to 4 p.m. Our invited speakers have a roundtable discussion opportunity, and down at the CHN building between 2 and 4, Dr. Hagenauer will be available, will be kind enough to be available for anybody who wants to follow up or ask any questions, advice and so on, we'll be there. And let us thank you again for.
Okay, thanks.